5i, velocity time graphs. Remember, position time graphs show the position of an object with the progression of time. Slope is velocity. With this straight line position time graph, we see that the object moves 20 centimeters to the right for every 1 second. The velocity is 20 centimeters per second to the right. Because it's a straight line, the velocity is always 20 centimeters per second to the right. So the velocity, also known as the instantaneous velocity, is equal to the average velocity. Because of the straight line graph, it's evident that the velocity is a constant. This object is moving with uniform motion. If we were to graph the position time data as a velocity time graph, the graph would be a straight horizontal line at 20 centimeters per second. This means that the velocity is uniformly 20 centimeters per second to the right at all times. It is not speeding up, nor is it slowing down. If we look closely at this graph, we notice that it's not traveling with uniform motion. It does not have a uniform velocity. We have used this example a number of times, and we know that this object is speeding up. It's accelerating. If we graph this data as velocity versus time, it would definitely not be horizontal, as it is accelerating. It is not traveling at uniform velocity. What would the velocity time graph for this data look like? Let's use this set of data to see if we can find out what the velocity time graph of an accelerating object would look like. We can see that the velocity is definitely changing based on the fact that it is displacing a greater amount for each time interval. When we plot the position time data points, we do not get a straight line. Rather, we get a smooth curve. This indicates that the motion is not uniform. It is accelerating. We can see that for every set interval time, in this case 1 second intervals, the magnitude or the size of the displacement keeps increasing. For the first second, it displaces 6.25 meters. For the second, it displaces 18.75 meters, then 31.25 meters, 43.75 meters, and the last second, it displaces 56.250 meters to the right. It is displacing an increasing amount for each set time interval. It is speeding up. We cannot calculate velocity or instantaneous velocity because the velocity keeps changing. We can, however, calculate average velocity for each interval of 1 second by calculating the slope created by joining the points at each second of time. The average velocities can be calculated by using the formula delta v divided by delta t. For the first time interval, it calculates to 6.25 meters per second to the right, then 18.75, 31.25, 43.75, and finally 56.250 meters per second to the right. Now that we have the average velocity, we can use the formula average velocity equals velocity final plus velocity initial divided by 2 to calculate the instantaneous velocities at each whole second of time. I have skipped showing you the calculations and have provided you with the values. At time 0, the velocity or the instantaneous velocity is 0. At time 1, it's 12.5 meters per second to the right, then 25, 37.5, 50, and finally 62.5 meters per second to the right. When we plot these data points, we get a velocity time graph that is a straight line. This does not indicate uniform motion. This is not a position time graph. This is a velocity time graph, and this straight line indicates uniform acceleration. If we look at our velocity time data, it can be seen that every second of travel, the velocity is increasing by 12.5 meters per second, or 12.5 meters per second to the right, which is equivalent to 12.5 meters per second to the right. Our final answer is 12.5 meters per second squared to the right. This indicates that for every 1 second of time, the velocity is increasing by plus 12.5 meters per second. In fact, acceleration of a uniformly accelerating object can be calculated by finding the slope of a straight line found on the velocity time graph. If we choose these 2 points at time 2 and 4, we can calculate the slope of the line. Now remember, because it's a straight line, we can choose any 2 points. Slope is rise over run. For these 2 points, it works out to be 50 meters per second minus 25 meters per second over 4 seconds minus 2 seconds, which is equivalent to 25 meters per second over 2 seconds, which calculates to 12.5 meters per second per 1 second, or 12.5 meters per second squared. Quickly to recap, a curved line on a position time graph represents non-uniform motion, acceleration. A straight line on a velocity time graph represents uniform acceleration. And if you calculate the slope of a line of a velocity time graph, you have acceleration.